All right. Let's start today by pulling up the right screen. Here we go. Okay, so I made some changes, indicating that I was not present in mind or body. I was like this in the bed the whole time. Thankfully, pretty sure I got it from my friend's kids, and he sent me some snaps that I won't repeat. But I didn't have that. So I'm really grateful in some respects. You can hear my voice isn't great. So thankfully, I'm going to keep this mask on as much as possible. And I'll try and give you direction slightly from afar instead of maybe touching on your consoles and whatnot. We're finishing up this conversation about boundary value problems, the shooting type problems, and we're going to get into the idea of boundary value relaxation, which is the natural next part to this problem set. And this is essentially the idea of holding the edges fixed and then evolving from there. And I think Andrew said, is that right? Were you gonna do this one?
Yeah.
Yeah. Okay. So I didn't move this over because I wasn't confident that that's what we talked about, but I'm gonna do that now. Okay. And so now we have a problem for next week. We got to fill that up. And then we have this thing called the code proposal. And so really what I'm looking for here is you're going to be seeing some types of problems, right? You're going to be seeing, solving, you already saw that we could solve a particle in a box using quantum mechanics. You will see that we will solve problems like electromagnetics problems. But I'm also going to show you probably on Monday, I'm going to show you like examples of what other people have done. And this includes like simulating orbits, so going from Earth to Mars. This includes like looking at how waves propagate on a string or in a room, like sound waves. This includes like how watching, for example, let's say you have a nuclear reactor and you want to keep track of all the different products. You could use that with a computer as well. So there's a variety of fun things you can do. Some folks did, have you ever seen fractals? You know what fractal is? Have you ever heard of the Mandelbrot set? Beautiful. And it's a set where as you keep looking at it, you get more and more detail every time you zoom in. And it's self-similar. So you start to see similar patterns arriving. If you've ever spent a late night with friends, maybe you put that on YouTube, like 7-hour version, and it just zooms the whole time, right? And like you turn off all the lights, right? And you put like, I don't know, whatever your favorite music is on. It's very cool. But we can understand it using something called regression, which can be done on a computer very easily. So we'll talk about all of those different types of ideas. And then what I'll ask from you by the end of the week is just to say, hey, I'm really interested in that topic. How would I do it, right? And you can kind of think it over. And then we'll go into spring break. I will intentionally be very absent. Okay, you can send me whatever emails you want. I need to just like unplug the computer, hit the factory reset, and then let it boot back up again. So my hope is that we will have, that's basically almost getting through chapter 9. And I'll tell you the honest to God truth, chapters 6 and 5, they don't hit like chapters 8 and 9 do. 8 and 9 are very physically based. They are, really deriving a lot from what the physics is about. Whereas like 6 and 7 are kind of really important in the context of you need them as a physicist, but they're not physically motivated in that they're like usually trying to solve a specific problem. And that's not always true. There's exceptions. But I find that presenting it in this way gives us enough time to really think about, okay, let's have some time evolution of blank. And that's like what we would be solving in these next 3 classes. So I'll just ask you to propose something and we'll go back and forth. And eventually I'll say, yep, that's a great idea. And then you'll start working on that on your own. It can start with a homework problem. And I'll put onto Canvas probably on Monday. I'll like show you what I expect from the problem as a whole. But it's like basically a homework and a half. And then you present it with a small presentation. Only 2-hour presentation. That's good. No one left. Okay. All right. Any questions? Okay, this class is high and tight today. This is a thing that I want to make you aware of. I already said this to some of you, but PK's lab is accepting applications to work on building and programming and flying drones this summer. And the benefits include research experience, mentorship opportunities, paid summer housing. That's fun. And you get to include it as research if you want to go on and do anything else. Right. So sometimes it's helpful to have that, like, hey, I did research on drones. Give me a job with real fucking drones, right? Or, I know how to build stuff. I know how to solder, right? So like if that's something that's of interest to you, you should apply. Applications go through the end of next week, I believe. And there's a QR code. And if you can't see this online, I guess just like screenshot that or whatever. Okay. That was exhausting for me. I don't know how it felt for you. I have less energy than normal. I will try my best today. I'll try to be clear. Monday's class, when I did teach it, so I don't know if you heard about this, I like taught Monday with a mask on. And by the end, I was just like, my brain was completely shot. So I will try to be as cognizant and clear as possible today. But if I make any mistakes, feel free to let me know. Okay. So I need 2 of you to sign up here and then here. And then the rest of them, I guess. First come, first serve. So there's a couple folks who already have 2. I believe Andrew will have his second today. Is that correct? Yeah, Andrew will have his second today. Let's fucking go. And I believe Isaac has his second. Right there. So they're leading the pack right now. Watch out. Okay, if you don't have one yet, nothing's gonna happen, but I'm gonna be upset. Okay? Not upset, just like disappointed. What's worse? Disappointed. All right, I'll be disappointed. Okay, any questions, comments, concerns? Okay, so let's remember, I know it's been like almost 13 years since we did any of this. Let's remember what we were doing. Will we finish this problem or no? I know that I was trying to find your bug and I don't know what to do. That bug just doesn't exist. It's weird. It never updated. So you could do the secant method, but if you don't know what that means, that's okay to just leave it as is. I'll accept that problem. So instead, let's talk about some physical motivations for partial differential equations. And in particular, just to set Andrew up a little bit, generally speaking, a lot of the things that we do in life, they're really not ODEs. They're not ordinary because they use a little bit of a lot of different dependent variables, right? So the types of work that we're going to be talking about here is much more broad. And so we're going to be able to apply it to a large variety of conditions. So far, we've mostly seen time differentiation. So we've been doing things like forward differencing to propagate from one point to another. And we saw at the end of last Wednesday that you could do, okay, let's start at one edge of the box and move towards the other edge of the box. And that would be like a way of differentiating in space. And now we're going to consider the effects of a 2-dimensional box and trying to solve all of it at once. And what that means is that we're headed towards relaxing towards a solution. And you'll see why it's not quite as relaxing as the spring break will be. Okay. Okay. Andrew, where do you want to start? Okay.
So today we're going to be talking about the boundary value problem and the relaxation. So first it starts with talking about the method of finite differences. And the solution involves solving Laplace's equation. And the problem will be considered in the 2D space to make the program run easier and more manageable and same with the big groups. And it also talks about the techniques for 2D and 3D, but they'll be used the same way. The method of finite differences is when you divide the space into a grid of discrete points. And if you go down on figure 9.2, it'll give an example of how that works.
Yeah, this is a great figure, by the way.
So the points are in boundaries of space and also in the interior, where the interior would be where the solution is at. But with this, we can use we could approximate the second derivatives using the finite difference formula. Some will have first derivatives.
Good. Do you want to walk us through any of this math? I could, but you don't want me to do that. Okay, let's just look at this first one. So what does this remind us of? This second derivative.
I see phi of x plus a, so that's the step forward.
Okay, hold on. So that is not quite where I want to go with it. We use some of the similar letters here, but here we have an expression like what you were thinking with Rangakata, where you like break it into two, right? That's a great way to think about this, but that's actually not what we're doing here. What we're doing here is we're looking at, remember when we did the finite difference? What did that look like? Finite difference, say d dt of phi. What's that? You guys forgot what I said? Finite difference. This is an approximation of the derivative.
That's a forward step minus the back step divided into some slice that we have.
Right, yeah. So for forward, it's like t plus h minus t all over h, right?
Mm-hmm.
And we said, well, we can do better. We can take a center step. So that's the one that you said, right? So you go like 1/2 step forward, 1/2 step backwards, divide by h. Okay, but what about this one?
We previously defined another function, right?
Yeah, so that's how we would do it if we wanted to uncouple the equations.
Yeah.
But if we just use this idea, and this idea says what? This idea says that the derivative itself is the slope. Okay, so this is the rise, how much it goes up in f over the run. What does the second derivative tell us? The curvature, right? The acceleration is also true, but in this case, when we're thinking just about shape, then it's the curvature. How many points do I need in order to find out whether something is curved? 3. Okay, so in fact, what we do is we grab where we are right now, f of t, okay, and then f of t minus h, and f of t, plus h. And we actually have to multiply by 2 here so that they're evened out. And we just do that. And this is all over h squared. Okay? So that was how we wrote it, I think, in chapter 5. And this was basically an approximation to the second derivative. This is not what we did to RK4. RK4 actually solved it in both cases, right? We would take this one, we would break down the second derivative into 2 first derivatives, and we would solve it this way, right? And that was actually better. But we're not going to do that here, because we are going to solve for all the points at the same time. And what I mean by that is we can easily go from d squared d t squared to d squared to dx squared, right? There's nothing special about time. It's just another coordinate. That kind of makes sense or no? And the same argument that we make here, we can make down here. So you see that instead of h, we use a, and that's how far away we are. So this is 1 to the left, or sorry, 1 to the right. This is 1 to the left, and this is where we are, divided by the spacing. And similarly, down here, this is y. This is 1 above. This is 1 below. And this is where we are. And this is the spacing, right? So using both of these at the same time, we can solve the entire shape at once. Does that make sense? Okay. Okay, let's keep going. Keep on keeping on. Okay, so here we are. That looks like garbage, right? Yeah, yeah. Right, right. Yeah, so this is the Laplacian operator, right? This is del squared of your scalar potential. And what's this step? Which direction is this? To the right, right? And this one? The left, this one?
And that's why I.
Is it y up?
Oh, yeah.
So it's up, down, and so what's this saying, right? So this is basically saying, okay, I'm standing here and I'm just looking around me and I'm saying, that's higher than me, that's lower than me, that's higher than me, and that's higher than me. So I'm curved this way and I'm curved that way, right? And it's just telling me about the different ways that I'm curved, right? Straightforward, no? It looks gross, it looks nasty. But if you just replace in your mind the word right, left, up, down, where I am, it's much more tangible, right? Okay. Success? Okay. And look, there it is. Same diagram. Okay, so what's next?
Yeah, so for that in simplification, function added at both breakpoints, so adjacent to x and y, and then go subtract 4 times the value at x and y, and then get that value squared.
Good.
And then when you combine equations 9.3 and 9.6, the Laplace equation will look like 9.7 right there. And the problem becomes a solution of a set of linear set of points.
Okay.
From a solution of a partial differential equation.
Yeah, so let's go back and let's remember what the fuck we're doing, right? Okay. So this is supposed to be Laplace's equation. Have you seen this before? What is it describing in this context of electrostatics? In particular, let's look at this picture. There's no charge inside. The edges here, here, and here are held at 0 volts, and only the top is held at V volts. So inside Laplace's equation says del squared of the potential is 0 because there's no charges inside. If there were charges inside, I would have to have that not be equal to 0. Does that make sense? Okay. And so what we're going to do here is we're going to solve for the potential inside, subject only to these boundary conditions and not due to anything inside. Does that make sense? So we start with this equation here on the right hand, or the whole thing, and we say I need to replace these two things and set them equal to 0. Right? Okay. So let's go back down. Here's our equation. Okay, go ahead.
For simultaneous equations, we can use a relaxation method, which is talked about in section 6.3.1. And those were originally used on nonlinear equations, but it can also be used on linear equations as well. And it also involves less work than the Gaussian limit.
Yeah.
You could then rearrange equation 9.7, which is the average of the values. And then we then guess the initial values. And then apply the 9.8 to solve our values of five on the grid and interior space.
Okay, so let's pause and think about that for a moment. What did Andrew, don't repeat yourself, but what did Andrew just say? Let's read this again. What does this say? Remember, we want to replace each of those phi's xy's with one of the things that we said before. Up, down, left, right, where I am, right? So what does that say in English?
I think the average of the thing.
The average of the change, good, and of what? What specific places?
Of all 4 points, right?
Exactly, right?
4 points around here.
Yeah. So where I am is 1/4, the average of up, right, left, up, down. Right?
You want to get another set of values, and you'll keep on doing it until 5 becomes a big value.
Yeah.
And then it also talks about the Jacobi, Jacobi method.
Yeah, the Jacobi method is a method of relaxation.
It's used to solve a Laplace equations, and it requires converging rather than diverging. And because situations where diverging becomes numerically unstable, the Jacobi method is always stable and gives a solution.
What do we mean when he says numerically unstable? Yeah, so it's similar to that. It can be too big or too small. But eventually you start at a place where everything's going fine, and then all of a sudden you end up with either really big numbers or like really small meaningless numbers, right? And it blows up. Does that make sense? So your approximation might be really good at the beginning, and numerical errors start to build up. They build up and they build up, they build up, and they give you trash. Does that make sense? Okay. Should we see an example? Or how do you want to proceed? Okay.
For the example, first you'll like label your constants and then put them here, which is like the grid squares. And use a volt to different top of the wall. And then you'll create an array and give it two multiple loops. And then you'll do a loop after. And then you'll calculate the value of the potential, give it the range. And, I was because you know how it says like for gain range +1. Could you just do like, were you able to just put like 101, or would you have to put?
You could, yeah, you could do 101, but then think about the places where this comes up, right? So you have 100 by 100. Here, you have 101 by 101. Okay, no big deal, right? This is from 0 to 100 though, right? So it doesn't run through the whole thing. And then it asks for when I equals m. Because remember that the 100th item, right, 100, gets you to the very edge. Does that make sense?
Yeah. To get the values of potential, you'll calculate the difference in those values. Then you'll swap the arrays around, and then it'll show it.
Good. Okay, so let's break this down. We're gonna pretend like we're adding comments here. First thing, great, good comments, right? Whoever wrote this, good job. What does this target mean? Yeah, well, accuracy between what? What are we trying to accurize? The what? Yeah, the voltage difference between what?
top and the bottom of the wall. And then we want the bottom to be 0, so we want to get somewhere near 0.
Well, the top and the bottom, the difference is always going to be V, right?
Yeah.
Because one of them is held at 0 and one of them is held at V. So in fact, what we want to be thinking about is here's how the problem actually works, okay? I have two arrays. I have phi and I have phi prime. They both represent one box. But what I'm going to do is I'm going to start off by filling out all of the values of phi prime based on all of the values of phi. Okay? Then I'm going to take the difference between them. And if the difference between them is so small that it's less than my accuracy, I'm going to say, good, that's close enough. My answer isn't changing that much. But at the very beginning, it'll change dramatically, right? So at first, it'll start off with one of them, and it'll have a big line here and nothing down here. And it'll try and connect those two, right? So every time that you switch, it'll have big differences. And slowly those differences will get smaller and smaller between every swap. Do you see? Okay, so let me show you how that works in the code, because it's actually really beautiful. Here's phi, that's the old array, and phi prime is the new array. I set the top of phi to V, and I'm never going to touch it again. And I do that with this very clever thing, where I say if I is 0, or I is M, or j is 0, or j is M, so that's all 4 edges of my boxes, I say, don't do anything special, just copy what was already there. That's a special one. This one here walks through I. This one here walks through J. J, 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 J. So if I'm not at the edges, what do I do? Say that again.
Find the value of where we're at by taking the average of the 4 points around it.
Exactly. So the value, the new value of where I'm going to be, so this is my new one over here. This location is due to the same location over here, but one up, one right, one back, one down. Divided by 4. Add them all up, divided by 4. 1, 2, 3, 4, divided by 4. Right? Okay. So then I go and I walk through this entire array, right? And I create all of these new values of phi. And now it gets tricky, interesting, right? So first, I take the difference between them. I figure out how big the difference is. If it's too big, I'm going to do it again. And then I do this really fun thing where I just swap the positions. Because this new one is now going to be the old one. And this one here, I'm going to overwrite with the new values. So that's the swap right here. Phi becomes phi prime, and phi prime becomes phi. Right? And then you do it again. That makes sense? Did I lose folks? What? It'll keep doing it over and over and over until the difference between the two arrays is smaller than your target. Right? Because if you have any single point where the difference is too large, it'll keep taking the difference. Now that's a little sketchy, right? Because we always said if you have a while loop, you got to make sure that it's working. So while you go ahead and start on a problem like this, make sure that you have something in here that doesn't let it run forever and ever and ever and ever. So you could have something in there just to check, like what does the first image look like? Maybe you print, right? Every 5 images or every 10 images, whatever you want to do like that. Does that make sense? Because if you only get to the very end to make the plot, you might run, a red circle and crash the cookout, right? Okay.
If you scroll down, figure 9.3, it'll show the density plot that you get from the program.
Yeah. And this is at the end, right? So up here it's bright,
Yeah.
right? Yeah, 0, right? Yeah. Good. Okay, oh, that's great. That really comes out well. We can talk probably about this one here when you have charges inside the box. But I think it might be helpful just to try that example problem first, like we normally do. And see if we can understand what we're doing. Okay, so let's break up into new groups. Zori, is anyone else online with you?
No, I think it's just me.
Anyone want to be friends with Zori? They're all fighting over it. Okay. If someone wants to jump online, that would be great. Let's break up into groups really quick, and we're just gonna give that one a try. The one that's the example problem, I want you to create it.